So I want to welcome you all to the second of our FEM at LLNL seminar series. You can keep up to date on the seminar series if you go to the mfem.org/seminar webpage. You can also find videos of this of this talk and other talks that we're going to give in our gallery and on YouTube. With that, I'd like to go ahead and introduce our second speaker, Robert Carson. Robert Carson is a computational engineer at Lawrence Livermore National Laboratory. He obtained a BS from Georgia Tech in 2013 and a PhD in mechanical engineering from Cornell University at 2018 under the advisement of Paul Dawson. His PhD thesis was on characterizing deformation heterogeneity during cyclic loading of polycrystalline materials using crystal plasticity. He joined Lawrence Livermore in 2018 as a postdoc and was converted to a full staff member in 2020. Robert's work at Lawrence Livermore is focused on the intersection between HPC systems and computational solid mechanics. Part of this work has involved leading the development of Lawrence Livermore's new open source crystal plasticity solid mechanics finite element code called ExaConstit as part of the ExaAM project in the ECP. ExaAM is an ECP project focused on modeling the additive manufacturing from melt pools all the way up to the part scale. In fused deposition, or sorry, not in laser powder bed additive manufacturing. As part of this project, he's also led the efforts to connect the microstructure to the part scale response, which has required coordinating a number of experimental and simulation efforts at different national research facilities. Outside of his ExaAM work, he's currently leading efforts to modernize and transition one of Lawrence Livermore's material modeling libraries to operate on a number of different heterogeneous computing architectures. So Robert, why don't you go ahead and take it away?
All right, I'm going to go ahead and share my screen. There we go. So everyone's seeing the correct screen, right?
Looks good.
All right, good. So today I'm going to talk about ExaConstit and its use in the ExaAM project. So to outline my talk, I'm going to first go over some motivation and overview of the ExaAM project, since I'm sure many of you guys are unfamiliar with it, especially if you're outside the exascale computing project or ECP. Then I'm also going to kind of have a brief overview of ExaConstit, especially since it's kind of a new code. I'm sure many of you guys aren't familiar with it, and especially if you're not in the field of crystal plasticity. Finally, I'm going to go, after that, I'm going to cover some of our GPU porting efforts, just because I figured it'd be kind of interest to some of you who are in the solid mechanics field, since that's not usually talked about as much. Afterwards, I'm going to talk about some of our local property calculations within the ExaAM projects and the kind of workflow that we created for it. And then finally, I'm going to go into some of the use cases of ExaConstit in other areas outside of, additive manufacturing and ExaAM project in general. So for those of you who aren't familiar with additive manufacturing, AM kind of produces these as-built metals that are characteristically quite different from typical manufacturing processes in both the microstructure and mechanical response of the material. And if we look down below, let me see if I can actually get the pointer right. Let's see, you guys can see the pointer,
right? Yeah, it's not. It's black, but it is moving around.
All right. There we go. There's the laser pointer. Okay, so yeah, these two in the left are AM manufactured parts. The microstructure from there is very complicated. It's definitely outside of the traditional manufacturing sort of things that we usually get that are nice, easy geometrical shapes that are pretty easy to model and aren't really complicated. And we kind of understand them decently well. And then AM just kind of throws us for a curveball. So we kind of have to start back a few steps to kind of figure out what's going on. And as part of that process, there's a lot of different modeling efforts out there. And the ExaAM project is kind of looking at modeling this from the ground up. And so we kind of want to be able to couple, as part of this project, we're going to be able to couple microstructure development and the local macroscopic properties together. And we can accomplish this through crystal plasticity models that utilize finite element methods. So the ExaAM projects overall, we're kind of focused on the regions in blue for the simulations of the additive manufacturing processes. So we're not concerned about the powder bed modeling efforts or optimizing for better performance of the parts or topology optimization. We're really just trying to constrain our focus onto the melt pool physics how that affects our microstructure and changes things, and then how that leads to our local property or variations in our local properties throughout our parts. And we are able to calculate those using micromechanical type models. And from our local properties, how that affects our part scale builds and the responses from there. So the overall goal, eventually once we have this kind of workflow, is to kind of help also the qualification of alien parts. That's kind of the long-term goal of these set of tools that we're building. So we're hopeful that we're able to get there with the new exascale computers that are going to be coming online. So a typical ExaAM simulation consists of roughly 5 different stages you can think of. So we kind of have a stage 0 where we do a rough simulation of our part builds using the thermomechanics of the initial part build. And that's going to be used as initial conditions for the various different thermal fluid solvers, which are then going to model the melt pool and all the physics that go along with the melt pool and the various different scan paths they do with the melt pool. And the various different properties that you have for the melt pool are going to feed into our grain scale microstructure calculations. So we're going to build up a microstructure during this stage 1. And once we have our microstructure, we can either do some further processing on it. So we can pass it on to another set of codes to do these late time microstructure evolutions, where you might try to model heat processing type techniques or stress residual type effects on the microstructure to get out what the late time microstructure from that might be. Or we can just directly bypass that kind of stage and go directly to the micromechanical set of calculations where we need to load up our microstructure in many different directions in order to get or probe out the response of the material at that local area in order to be able to parameterize a macroscopic model that will be used in our part scale simulation. So my work is really focused on this stage 3 here. So I'm really focused on getting out the local properties so we can have a better informed full part scale build. So ExaConstit is a relatively new nonlinear quasi-static implicit fine element solid mechanics code. Of course, it's built on MFEM. Development of it roughly began back in 2018, and then it really started picking up in 2019 and 2020 for the ExaAM project, and now it's kind of used in a few other projects as well. So it's started to evolve outside of just the ExaAM project. It's based on a updated Lagrangian formulation, so we're velocity-based codes for our primal variable that we're solving for. I'll get into our reasons for that a little bit later, but that's just to give you a heads up. We natively support a wide range of elements thanks to MFEM. We're able to support complex parts and non-trivial / changing tertiary boundary conditions within the code. And we're also open source and we're available at the Livermore GitHub page. So, of course, since this is a exascale computing project, or designed for an exascale computing project. It's designed with exascale computers in mind, but we still want to be performant even on desktop machines. We want to be able to run on, whether it's your Macs, your Windows, or whatever Linux cluster you might be running on. We still want to be able to support those different systems, so you can run and start doing research type problems with it as well. We're always looking at adding new features, workflows, and post-processing tools. A lot of this is also dependent upon what our users' needs are. So we kind of prioritize different features depending on what our main users need. Of course, I mean, since I mentioned we're looking at a lot of crystal plasticity type simulations, our bread and butter, of course, is going to be crystal plasticity type problems. And for these crystal plasticity models, we actually use an external library also developed initially through the ExaAM project called ExaCMEC. We've open sourced that library as well for those who are interested in crystal plasticity type models. We have that, and you can use that for things outside of finite elements as well. I will mention that the models that we have in there can be upwards of 75 to 90 times faster than comparable crystal plasticity type simulations within Abacus that make use of UMATs, and that's one of the reasons why is because of the fact we can run on the GPU. But I will also mention that within ExaConstit we also support UMATs. So by having this UMAT framework within there, we're able to run a lot of industry and research models that already exist, which is nice. So just to give a brief overview of kind of what a typical model kind of looks like for crystal plasticity, I'm just going to cover this briefly. Don't worry about the details too much, but I just want you to be kind of aware of what the kinematics and physics that we're kind of solving for. So we're a large strain single crystal elastoviscoplastic model with a small deviatoric elastic strain. What this more or less breaks down to is our deformation gradient can be multiplicatively decomposed into an elastic and plastic portion. So for those of you who aren't familiar with the deformation gradient, it's just simply it's just simply a mapping from your undeformed configuration to a deformed configuration. So we can multiplicatively go from the plastic to the fully deformed using So one of the things though is, I mean, a lot of people kind of just, once they have the deformation gradient, they'll go and do what they need with it. However, our constitutive equations for the plastic flow kind of depend on us further developing our kinematic decomposition. So we actually need the velocity gradient. The velocity gradient is the time rate of change in the deformation gradient. And it's given in our first line here in the current configuration. We can also describe the velocity gradient in this B hat frame here as L hat P, which is made up of a spin term of our lattice and the rotated portion of our plastic velocity gradient. And our plastic velocity gradient, which is given in this line here, is directly related to the combined shearing of our slip rates or our slip systems. And our slip rate can be described using various different equations, but for a lot of the stuff that we're doing here, we're just going to be making use of a basic power law, where for example, tau here is our resolved shear stress on a given slip system, and then G is our critically resolved shear strength for a given slip system. And I mentioned earlier that we have this small elastic strain assumption. You can replace your elastic left stretch tensor with this set of equations here, and you can simplify everything even further down. So it's all represented with your elastic strain. But the reason why I just want to bring this up is just to be able to highlight that the evolution of our elastic strains, lattice rotations, and our slip rate are all dependent on one another. Due to this fact and the fact that some of our set of equations are highly nonlinear, solving for the updates of our states can be quite computationally expensive and a bit more expensive than your typical constitutive equation for your models. So now that I've kind of covered the basic models, I just want to cover the basics of our finite element formulation. So we're really not doing anything crazy here. It's just your typical nonlinear solid mechanics finite element formulation. For those who aren't as familiar with it or what the nonlinear form might look like, it really looks, quite similar to what a linear elasticity type formulation might look like. Except for, with your tangent stiffness matrix, instead of, having your elasticity tensor here, our material tangent stiffness matrix is, the derivative of our stress with respect to our deformation rate. And our deformation rate is just the symmetric portion of our velocity gradient. I mentioned earlier that we're making use of our updated Lagrangian formulation. And what this means here is, just that the fact that our mesh nodes are always in the current configuration. And because of this, we really want our primal variable that we're solving for to be the velocity field rather than displacement. So, this is a slight variation from what we're doing, but it's mainly due to the fact that, for our kinematics, it's a lot easier to describe things with the velocity field rather than the displacement field. And then, of course, for our updates, for our mesh nodes, we're just doing a simple integration scheme here, so nothing crazy. So, like I said, a lot of the things that we're doing here are fairly simple. It's more our constitutive equations that are more complicated. So, our finite elements are pretty simple, relatively speaking. And due to that, we're able to make use of a number of different formulations when we're kind of looking at assembly operations. And when we wanted to transition to the GPU, we had to really step back and look at how we were doing things in order to make the most out of our performance of everything. So ExaConstit, I will mention, originally had the material model calculations tied in with the linearized right-hand side calculations and the computation of the stiffness matrix, which is fine when you're running on a CPU. And you only have one set of assembly operations for your finite elements. But it really starts to not be very portable / work really well when you want to start looking at different assembly operations that can get you up on the GPU. So we had to kind of take a step back and look at how we were doing things and kind of refactor. So after refactoring everything, we kind of split up our code into kind of a setup phase, a pre-processing step for assembly operations, of course, our right-hand side calculations, and then our gradient calculation / operation. So I'll just briefly mention what our setup phase looks like. So during the setup phase, we're just going to be calculating the necessary parameters to use within our material model. So we need to get everything that we need from our mesh and our displacement and our velocity field that we might need in our material model. Then we have a pre-processing stage for our material kernel, so calculating all the things that we need for that. We have our material kernel stage where we're going to go and run our material kernel, and then we have a post-processing stage for our material kernel. And during this stage, you're going to perform whatever steps are needed to take what you've gotten out from your material kernel data into a format that can be used by the rest of the code. And for the pre-processing and the post-processing steps, we make use of infim for all loops in order to abstract, or for parallelization abstraction. This made things really simple because we didn't really have to worry about supporting or having a lot of duplicate code for various different parallelization strategies. However, for our material model, we left it up to the library to decide how it wanted to do its own parallelization strategy. And I'll just mention that for ExaCMech, for example, we make use of Raja internally for that, and that's allowed us to support a lot of different parallelization strategies, such as the host, OpenMP, CUDA, and HIP. So I'm definitely a fan of Raja. So we have also done a partial assembly formulation I will mention. However, I figured it'd be best just to go over our most efficient formulation for our set of problems. And for that, we looked at an element assembly formulation rather than the partial and the full assembly, especially to get on the GPU. And so we kind of went back and we looked at a lot of the original literature for the solid mechanics field. And it turns out that back in the 70s and 80s, there's a lot of really nice set of papers that were written that went and actually were like, all right, here's how you want to do things efficiently, and so you're not hitting memory bandwidth type things. You're really well, advantage, or you're really able to take advantage of the machine. So we didn't have to start from square one. We were able to make use of those papers. So for the internal force, we just make use of a partial assembly type formulation. So we split this down into the below, where of course this is like the summation over all your quadrature points and elements, but it's just the determine the Jacobian, the weight of your quadrature points, your isoperimetric, or the gradient of your isoperimetric shape function, and the adjugate of your Jacobian times your stress tensor. So nothing complicated there. Where things kind of get a little bit more interesting is when we look at our tangent stiffness matrix. You were able to break it down into a lot of subblocks when we're doing computations. And this allows us to really efficiently build up our tangent stiffness matrix, because of the fact that we're able to just work on small blocks of code at a time rather than doing very large computation or matrix multiplication type thing. And so we're able to do a bunch of small ones. And you could even further specialize these type of operations for tensor type elements, where you even further break things down in order to get an even larger performance gains than kind of what we have now. And then I will just mention that for another set of integrations that we've kind of done, we also added in like incompressible material support with an ExaConstit. And for this, we were just using a very typical B-bar type formulation. And due to this, previous shape function gradient became a bit more complicated. And so our integrator also became more complicated. And, this required us to be a bit more careful about how we implemented everything to make sure everything was done correctly. But that's all within ExaConstit. It's all up and running. And the nice thing about this is it's able to bring our linear hexahedron element response much more in line with what we see from higher order elements. I also mentioned one of the nice things, at least on when you're running up on the GPU, is the runtime between your full integration approach and this incompressible integration type approach is roughly the same, which is a nice bonus. So now that we've implemented everything on the GPU, how well are we actually doing? Well, we're actually doing pretty well. So we have, after we implemented everything and have a fairly efficient GPU implementation, we see, currently about a 15x speed up between the GPU and the CPU when running things on, Summit/Atlassian type machines. And when we look at kind of the scaling and performance across all our different assembly operations, the seal down here is our element assembly. These operations here kind of our partial assembly, and then up here we have our CPU assembly. So we can really see that we had a huge gains from moving to our element assembly. And then if we actually look at our element assembly itself, and we actually do strong and weak scalings, we can see that we're not doing too well in the strong and weak scaling regime, and part of this is just due to the fact that we have a large startup cost for our set of simulations when reading in our mesh and partitioning it. However, I'm pretty hopeful that recent work that's been done within MFEM is expected to drastically improve this area, and I expect us to have even better strong and weak scaling. And I would just like to thank Vesselin for that work. I very much appreciate it. And then also, we'll just say that we've been porting ExaCMake over to HIP this past year. We have it up and running on the early access machines, and we're currently working on the ExaConstit port, and I expect that to be done probably within the next month or two. So one thing I kind of want to talk about is after you kind of make the shift from running on the CPU to the GPU, it's kind of nice to take a step back and kind of see where your computational shifts have moved when you make that shift. So I made use of Caliper in order to annotate and do a performance annotation to kind of or get out the performance percent time that we kind of spend in all our different kernels. Majority of our kernels, or majority of our time is spent in just these set of kernels. We can see that pretty much 99% of our time is spent in them, for both the GPU and the CPU. So one of the things that we can see, right away is our Kirillov solver is still dominating our runtime, which is kind of expected for implicit type simulations. So there's nothing shocking there. But one of the big things that we can see that's a bit surprising is our MPI calls go, more or less triple in the total amount of cost that we're kind of spending on MPI calls. And talking with some of the members from the MFEM team, we believe this might be partially due to the fact that for the MPI libraries, the device-to-device calls aren't the most performant. So or at least this was a year or two ago when I was talking with them. So there's probably some gains that can be made here, and just from having more performant device-to-device calls. However, I will mention that even though the MPI times are costing us quite a bit more, it's still 40% less on the GPU than on the CPU. So we still have a win on the MPI calls. It's just they take up a larger percent of our time. And if you really wanted to kind of hide some of that time from your MPI calls, you could look at something like or you could look at something like communication hiding Kirillov solvers in order to reduce the MPI calls that you're making. So now that we have this nice performance code, what are we going to use it for? What do we really need it for? So, within ExaAM, I've kind of mentioned that we need these local properties to be calculated throughout our parts. And each one of our local properties type calculations requires us to run a ton of different crystal plasticity simulations under varying load conditions, temperatures. And the reason to do this is because we really can't get away with just running one simulation for an AM part. And the reason why is if we look at our deformation field over here, it's very complicated. There's a lot going on, and our response from our material is anisotropic, so it's not a nice isotropic type behavior where you can assume the response is equal in all directions. And due to this fact, we're kind of wanting to parameterize a macroscopic model. We kind of want to look at a more complicated macroscopic model than something like a J2 model. And I'll get into that a little bit later. But first, I kind of want to talk about, one of the things that we need to do before we start running all these simulations is we kind of need to talk about what a representative element is for our part, or for our microstructure that we'll be using during all these simulations. So about back in 2020, we ran a set of studies where we used the similar scan patterns from the NIST AM bench problem, which is kind of our problem that we're trying to simulate within the ExaAM project. And what we did was, we ran the, we had the same scan patterns. We generated a microstructure using the ExaCA, which is our cellular sonoma code that we have, which is also open source, I'll mention. And then we ran a fairly large sample that's about 500 micron cubes. We made it very well resolved with roughly 27 million elements within this cube. And then we kind of looked at what happens when we decrease the domain size and decrease the amount of grains that we had within each one of the domains. So we decreased it by thirds each time. So we went from 500 microns to 330 to 166 micron cubes. And I'll mention that even though we were reducing the domain size, we still had fairly well-refined meshes. Even the small microstructure down here, still had 1 million elements in it. And then, first, set of simulations that we ran, we only took out things to 5% strain, just because of the fact that within, our projects, we're not really concerned with large strains, just due to the fact that we're really looking at that elastoclastic transition region in our material. So we don't really have to go out to large strains in order to examine that. So when we did that, what we found was, this medium cube was below 5% error for the entire loading history. So our represented volume should be somewhere between, what the medium cube is and the large cube. Just because of the fact that, we do kind of see they're kind of growing as the sample starts entering fully developed plastic flow. But if you really wanted to, we could go, get away with potentially something that's medium cube. However, and the reason why I mentioned that is the small cube, it didn't start out too well. It started around 6% error at the beginning, and then it just continued to grow that error as you got further and further out. And I will mention that the main difference between all of these responses was largely driven by the crystallographic texture between the materials. And I'll get into a little bit later about what crystallographic texture is, but that's just, you can think of it as a directional dependency on your material response. So it's quite important when you're modeling materials, especially when you're doing something that's not necessarily isotropic. As part of the study, I also kind of looked at effects of mesh coarsening because, let's face it, not everyone has access to a supercomputer, and they can't run, a 27 million element simulation just like nothing. So I wanted to look at, what happens when we start coarsening these meshes to something that would be more reasonable for, research labs that aren't, that don't have access to these large machines. So I went and took our original microstructure and I coarsened it, several different layers. And by coarsening, I mean, the kind of different levels I looked at, were 2, 3, 4, and 6 different levels of coarsening. And levels here just refer to the fact that, or refer to the number of voxel grains or neighboring voxel grains that were averaged into one voxel into the coarser mesh. And what we can kind of see is that, by doing that averaging between the original and the coarser, we lose out a lot of that finer details, but we still have, or we still retain a lot of the, major columnar grains that we kind of see. So, when we look at the macroscopic response, more or less all of them were, the same. We only saw 3% deviation between all the different cases. And this was largely due to the fact that the crystallographic texture was largely the same between them. And, if we were just looking at, or we were just concerned with the macroscopic stress strain curve, this tells us we can get away with, fairly coarse meshes if we need to. However, as part of this project, we're also kind of interested in, potentially looking at porosity type models or parameterized porosity type models with our macroscopic simulations. And because of that, we kind of want to use something that's not super coarse, just because we want to capture the distribution of our hydrostatic stress within our material decently well. And so we really don't want to coarsen it so much. So that kind of answers the question about our RV. But as I kind of mentioned, we don't really want to use a J2 type model earlier. And the reason why is, and we kind of saw this earlier, was I mentioned this strongly textured type effect in our material. And J2 models just don't do well or good well with that because they assume everything's isotropic. And when you're looking at macroscopic type models, there's a lot of different ones out there. And this is due to the fact that within manufacturing, people looked at wanting to model things such as rolling processes for sheet metals, due to the fact that they know sheet metals have a very textured response that's very orthotropic-like. And another area, for example, is these as-built materials also have a very similar orthotropic type response. It's very orthotropic in the build direction and then the transverse. However, you can kind of mitigate some of that texture response if you do post-build heat treatments and manufacturing processes such as HIP, which can kind of get you to more uniform texture type responses. Another reason why you might be kind of interested in some of these anisotropic responses is it can also be advantageous to your performance of your part. You may not need an isotropic response. You can actually design it to be more anisotropic. And I mean, that's what they do in composite type builds all the time. So as I mentioned, that there's been a lot of research in these kind of anisotropic yield surface type models. And one of the guys who really did a lot of work at this was Bartlett and several of his associates. Over the years, they've done a lot of work to try and better model sheet metalling processes, just because people really don't like wasting material. So having a better model for how the sheet metal forming kind of goes really helps. So he created a model called the Yield 2004 18P model, which is a really clever name, I know, but it's just because of the fact that came out in 2004 and it has 18 parameters. And this model is largely orthotropic with some out-of-plane behaviors that's able to capture. I'll mention that some of the nice properties of it is the fact that it can reduce down to several famous models, such as Day2, your Hill yield surface, and your Tresca yield surface models. So for the ExaAM project, that seemed like a pretty good fit for us because of the fact that we can use it and we can model these anisotropic behaviors, and then if we want to, we can also use this exact same model to drop down to some of the simpler models to see what our different responses are. And I will say that the past year, I spent a lot of time implementing this model into one of Livermore's in-house material model libraries. We have that up and running now, and I do have plans of actually having an open source version of it within ExaCMech within the next year or so, so people will be able to use it. So how does this anisotropic yield surface model kind of fit within the AM workflow? So the Bartlett model traditionally has been parameterized using experimental data. However, this data is typically not cheap or easy to obtain. But when you think about it, simulations are pretty cheap, relatively speaking. You just have to run a bunch of them on a cluster. They're not too hard. So because of that, crystal plasticity simulations kind of come to the rescue here. So we don't have to run all these expensive experiments on them if we don't need to. So ExaConstit is going to drive all our simulations along with some workflow tools that we've kind of written in Python. And I'll mention that these workflow tools that I'm going to talk about in the coming slides, I do have plans to eventually include them in the ExaConstit repo, but we're just kind of cleaning up and finalizing them. But you can contact me if you're interested in them, and I'll see what I can do to get them to you sooner. And then our microstructure, it's provided by an outside code called ExaCA. That's also, like I said, it's up on the Livermore GitHub page. It's able to generate these nice microstructures for us. And then for optimization type things, we're just using simple SciPy optimization functions, although I'm sure people who are more familiar with optimization type things could probably suggest better frameworks for the type of things that we're doing. So our workflow for connecting stage 1 to stage 4. So the local property calculations can be kind of broken down into 3 different stages for each RV. So we have kind of a pre-processing stage where we take in our microstructure, do some processing of it, get out a mesh, and then kind of create a test matrix. We then pass all that data that we kind of generated over to our simulation stage where we kind of have a job generation script that goes and generates all the jobs that we need and then runs them all. And then once we have all those simulations run, we're then able to then slurp up all our results and optimize our microscopic yield surface parameters using those results. And then we're able to repeat that kind of process for each different terrains that we're kind of are interested in. And then once we have that, we can feed these parameters into our microscopic part scale model if we need to. And of course, you can repeat this step for each RV. And I will mention that each RV is kind of separate from one another. They don't depend on one another. So this workflow can really scale out and is what I think you consider a embarrassingly parallel workflow. So we actually worked with the ExaWorks team on this workflow for the ExaAM project, and what they kind of helped us do was swap some of our LSF jobs type scripts over to Flux. And due to this fact of moving from LSF to Flux, we actually saw 2-time improvement in our job turnarounds, which is a huge win, especially when you're wanting to run potentially thousands of simulations on a system like Frontier. So they've been a lot of help for this type of work. And I'll just mention that they have an SDK out on GitHub that has a lot of different workflow patterns out there that could be useful to various different peoples. And I also mentioned that Flux is also a pretty nice tool that's also up on GitHub. So I'm just going to get into some of our steps, just because I think it might be of interest to some people in the crowd. So for a pre-processing step, yeah, it's pretty simple. So we have a command line interface script that takes in the microstructure, it generates a mesh, and then it pretty much just creates a test matrix. You can provide it multiple temperatures and their corresponding property files. It can coarsen the microstructure if you need it to, and then it can also generate the test matrix, which will later be slurped up by the job generation script. And this is just kind of what a stereotypical command line interface might look like when you're doing it. So it's fairly simple. The mesh generation, it's very simple. It's just calling out to an external executable, which is, we'll also mention, is based on MFEM. And this is generated by the ExaConstit library as well when you build it. And then our test matrix, I didn't include all the code just because it's not super relevant, but it's pretty simple. It's just essentially a Panda data frame that we created, and we save off as a CSV file, and then we'll later just slurp it up back in, or back up again as a Panda data frame during our job generation script. So this is actually something that I think is kind of neat. So, it doesn't actually take a lot of lines to create something to generate a lot of jobs for you. And, I was able to make a nice, simple job generation script that takes in our test matrix, that takes in a master option file, and then kind of a job submission file for you. And then, it goes and, has each simulation in its own unique job directory. And within that job directory, we have symlinks to all our shared original data. So we're not thrashing the file system, copying a lot of data across. We just are pretty smart in using the symlinks. Our master option file has just some simple regex searchable expressions in it that can then be replaced by values from our test matrix. And then, we're internally able to support, either LSF or Flux type job submissions. And, for example, swapping between LSF and Flux, it only required 5 additional lines of code. And we could just as easily also extend this to SLARM systems as well. And then finally, it generates a master job script for you that you can then have it submit all your jobs for you, or you can tweak it a little bit more if you want to. And the nice thing is, something like this job generation could easily be extended to, parametric type studies. So this job generation isn't unique just to my type of problem, and you could easily use it for other type of things, that aren't, this ExaAM workflow. And in fact, when you look at the main code logic for this job generation, it's only like 30 lines of Python code. So I just thought I'd bring that up just because it's pretty simple and it's not too complicated. So once we have all these jobs, we're able to run a ton of simulations at once. And from all the simulations, we get out a ton of data, along with the stuff that we need from our microscopic model. And some of the nice things that we get out from these are some pretty interesting visualizations of the deformation of our AM material. And I just wanted to show a couple of videos of the various different loading conditions. And we can see that the deformation is rather complicated. So once again, this is just showing that importance of looking at an anisotropic yield surface. And these are also some of my favorite videos, or just the simple shear ones that I thought I'd share, just because they're the deformation is pretty crazy that you see develop in them. And it's definitely not uniform. Yeah. So lastly, I'll just briefly go over, optimization procedure is pretty simple. For each RV, we kind of load up the necessary data and then calculate, what we need to to feed in our optimization script, and then we just let our simple optimization function do what it needs to do. And that usually takes a bit of time, so it's usually a great time to go grab some coffee or do some other work. And then we can repeat this procedure for each different temperature for our RB, and we instantiate the initial parameter set for the macroscopic things using our previous temperature as initial guess. That usually helps speed along our convergence a bit faster. So that's pretty much it for the ExaAM type things. We have this workflow up and running, and it's we're able to run our simulations that we need to now. So I figured it'd be good to also mention where ExaConstit can be used outside of just the ExaAM project. So some of the areas, you can use it to quantify variability and microstructure effects on the material response. You can look at it for fatigue applications in order to understand deformation mechanisms at the microscale. This is also a very important area for research. You can use it to create better material models to capture single crystal behavior, for example. You can use it to model geological materials to better understand how Earth's lower mantle deforms. You can use it to couple experiments and its simulations by using techniques such as forward diffraction techniques, or you could just use it to model such things as texture evolution of materials over large deformations. So I'll get into a couple of these real quick. Aaron, how am I doing on time?
You're a little bit over, but like I said, we've scheduled an hour and a half for this, so,
Okay,
it's 10 to the hour.
Okay, so I'll probably skip over some of these, but I'll just mention the variability. So while we did do this one for an AM processes, I'll just mention that varying processing conditions can lead to, of course, different microstructures, which of course can affect the micromechanical response of material. And if you want to study all of this, it's a very wide parameter space, so you're usually best off to only focus on a few aspects when you're varying processing conditions. So Matt Rochigo, who's a member of the ExaAM team, led up the study of varying the parameters for the microstructure processing conditions using ExaCA, and it generated a bunch of different microstructures. And I helped look at what the difference of the micromechanical response was from these varying microstructure conditions. So during the study, he kind of looked at varying the AM substrate diameter. So that's your base plates, grain sizes. And then he looked at varying the nucleation rates for your grains and how that affects the microstructure. So he got a lot of different microstructures depending on how the parameters were varied. But one of the things that we found was even though we varied a lot of these, and there were some large differences in the average grain diameter, you really only saw minor differences in the stress strain response in this 5% strain that we're kind of looking at. We only saw a max difference between, or 6% max difference between the min and max response when we were just looking at the microscopic response. Although we did see a much larger difference, or much larger set of differences when we started looking at the intragrain response, which was expected. Next, I'll just mention that we can also use it to simulate single crystal responses. So capturing single crystal responsive metals is often challenging, as traditional crystal plasticity models were designed to capture responsive polycrystalline metals. So they often neglected some of the physics that go on within single crystals. So we have an LDRD set up to better examine this area and are working on promising new model formulations. But I just want to kind of show, we can model the deformation of single crystals, and we kind of do this doing compression type things. We see some nice buckling form in our materials, and when we actually looked at the experimental data for these things, for these single crystals, we actually see that buckling as well. So it's really cool seeing our simulations actually capturing some of these experimental responses. I'll just kind of skip over these next two. As I kind of mentioned, you can capture crystallographic responses in the material. And this is just kind of showing that, here's kind of the initial crystallographic texture. Here's it after we deform it hugely. And we see that our material does start evolving its orientations, and we start seeing much more anisotropic response from the material over time. Next, I'll just mention that you can also simulate high energy X-ray diffraction experiments. And that's pretty cool because of the fact that these high energy X-ray diffraction experiments are able to get you at the intergrain heterogeneity for either your lattice orientations or your elastic strains for each grain. It can also give you a few other things as well, but it's pretty cool that you can do a direct comparison between the two if you simulate your high energy X-ray diffraction experiments using from your crystallosity simulations. So just in summary, ExaConstit is an open source crystallosity finite element code built on MFEM. It's highly performant on systems ranging from desktops all the way to systems such as Summit. We've implemented several different integrators for GPU support and different material models as well. Over the past year, we've created a workflow in collaboration with the XWorks team to efficiently run large number of simulations, needed to calculate local properties in the ExaAM project. And then I'll just mention that ExaConstit is also well posed to tackle a wide range of research topics within the crystal plasticity community. So yeah, that's it. Does anyone have any questions?
Thanks, Robert. Why don't we go ahead and thank our speaker real quick with some virtual claps first. Would like to open the floor to questions. Go ahead and unmute yourself if you want to ask a question. Or if you want, you can throw it in the chat.
Yeah, I've got the chat open so I can see the stuff.
So in the meantime, I'll go ahead and ask one. So you know, you've made ExaConstit open source, and you've got these workflows. Has anyone you know, outside the laboratory grabbed onto it yet and done some cool stuff with it yet?
So we have a couple collaborations with external laboratories that are looking at some interesting stuff. So we have some that are looking at some automatic material parameterization type workflows, which I think will be really useful to the community. And as I mentioned, you know, we can simulate these high energy X-ray diffraction type experiments, and we have some collaborators that are looking at extending that and looking at that. So, you know, the community is starting to grow. I'm very much interested to see, you know, as it starts growing, what people are able to do with it.
Absolutely. It looks like Mike Puso has a question. You want to chime in, Mike?
Yeah, go ahead.
Yeah.
Mike.
Hi, Robert. So like on your return mapping, it's typically non-linear, and so you have to do iterations, and I don't know how fast these models converge for you, but I mean, did you implement an implicit time integration scheme for the plasticity, or did you do an explicit
It's
update?
all
It's all implicit, right? So then you have sort of a bottleneck, I guess. You know, you always have some stubborn element that, you know, doesn't want to converge, and the rest of the guys got to wait around for them on the GPU. Did you do anything special to treat that, or did you just get stuck with that?
It's usually not too much of an issue, as long as you're smart about kind of where you're taking your time steps. So I mean, really the trickiest part is right here along the knee of the curve when you go from that elastic to plastic transition. And when you do that, you know, you have a lot of variations in kind of how the materials start, you know, either plastically flowing. And so you can see some lag there, but I mean, once you're past that, I mean, it's, you know, it's usually not too bad. I mean, the materials are usually fairly well behaved. Although, I mean, of course, I mean, when you start looking at more dynamic problems, it becomes much more tricky. And for that, you know, I've looked at different solvers for things, but I can talk to you about that offline if you'd like.
Sure. Yeah, sure.
Are there any other ones?
Hey, Robert, this is Tanya.
Yep.
I have a quick question. So thank you first very much for the talk. From the perspective of ExaConstit or the ExaAM project, what are the big outstanding issues for you? What are the things that you'd like to see progress on in MFEM, in theory, in software in general?
So, I mean, you guys have been pretty great about supporting some of our needs. I think, some of the stuff that we need to kind of work on, and, I have to kind of find some of the help, or some of the time to help too, or just kind of the multi-material support. That I definitely have ideas for how to do it, and I just need to kind of implement them as kind of a work in progress type implementation, or a MVP type implementation for people. But largely a lot of the stuff that we need is kind of there already.
Okay, I just wanted to check.
How about do you have plans for non-local materials, or is that that's maybe farther down the road?
So at least within this one, I don't have any right now. That might be something that I have ideas for how I would like to do something like that. But it'd be a question of, of course, finding the appropriate funding sources to implement it.
Sure. Yeah, I asked that one in particular because it kind of steps outside of the framework we've kind of built up. So we'd have to think pretty hard about how to add that.
Yeah, at least within the crystal plasticity type framework, the non-local type formulations are more, there's a couple of different ways to do it. But it would be essentially, having an additional nonlinear or global nonlinear solve at your constitutive equation update. And so there's a ways around it, but I think it'll just require some research and development effort.
Sure. It looks like we've got a couple questions coming in through chat. Thomas Helfer, would you like to chime in?
Yes, so thank you, Robert, for the talk. I had a very similar question for the first one. How do you handle if you locally your constitutive equation doesn't converge, because I assume that you're doing some sort of local Newton method, something like this, to solve the implicit the constitutive equation in an implicit way. But what if it doesn't converge?
So I really haven't run into that issue, just because we have a pretty robust nonlinear solver. So we have a trust region Diogleb type approximation solver.
Yes.
That one, for at least these type of problems, is pretty hard to not have it converge. But I've run into a couple of situations where there's ways around it. So some of the ways to do it is, we kind of decouple the internal state variables and don't have them as strongly coupled within our nonlinear solve, and that's usually good enough to get everything to solve. But right now, if it doesn't solve, at least within this one, I haven't implemented a time cutback to do it. So that would be the next logical thing to, if the material state doesn't converge,
Okay.
reduce the time step.
Well, so the iterations do, like, so you get stuck on one element and all the other elements have to wait around, Gauss points or whatever, because it does affect your scaling though, right? Did you look at that?
I really haven't seen, like I said, it's usually not an issue. At least of the stuff that I've looked at. Most of these are fairly well behaved. They internally, the stuff converges within a couple iterations. Sometimes some that are really bad that might take 50 plus, and unfortunately you're stuck with some of that. But it's still an active way of how to best do that, I'd say, on the GPU, and I have an ideas, or I should say I have ideas for how to do it. And I am working on it, but that's a project outside of the ExaAM project that I'm looking at it.
All right, I think we have another question in the chat. Hilo Lee, do you want to unmute yourself and ask it?
Sure. Thank you very much. Robert Carson. I'm from Morgan State University in Maryland. Yeah, I'm actually doing something in two-level Schwartz overlapping algorithms for proelastic mechanisms. But actually, for your problem, your physics, have you ever thought or tried any domain decomposition efforts?
So when you say domain decomposition, can you clarify that a bit?
In general, whatever that is, non-overlapping or overlapping, definite or indefinite intrinsic structures, spectral structures, and also you mentioned non-local a kind of wave propagation. So you may consider something interesting, I guess.
So we're not really looking at wave propagation type things, since this is a quasi-static code. So I think based on what you're kind of describing, I'm going to say that no, we haven't really looked at any domain decomposition type efforts. You know, that's probably a bit outside my wheelhouse. So, you know, if someone was interested in that and, you know, understood it a bit better than I do, you know, I'd be interested to see what that would kind of look like. But we haven't looked at it.